Welcome back to the video playlist for dynamic programming. In the last video, we solved the longest common subsequence problem using a recursive algorithm. In this video, we're going to take that recursive algorithm and instead make it so it is a dynamic programming algorithm. So, actually, we're going to return, same thing, I'm going to change the name of this function so that it's LCSDP, and as before, we need to make a table that we can look values up in here. And so I'm going to make a vector. Now in this case, there are two arguments in the recursive function that change, so we need a two-dimensional array here, or a vector of vectors. The arguments are themselves ints, and we return an int. So note that the arguments need to be ints because we're using them to look up in the vectors. The return type is the type that needs to be stored in here. For the rod cutting, we made the return type a double, and so our vector was a vector of doubles. Here, this returns an int, so our table is a vector of ints. And how about I call our table T, and the length of, I'm trying to decide how I want exactly to set this up. Yeah, we'll go with this for now. Okay. Let's go ahead and let's make it the right size. So I will make it so the first dimension is s1.length, and then the second dimension is going to be full of vectors of s2.length to make sure that's happy. The value this is going to return is simply the table looking up at s1.length minus 1 and s2.length minus 1. I'm writing C++, so I need to put a return on that. Okay, now what? Now we need to write the loop that goes around and fills this up and has this logic from the recurrence relationship inside of it. So I'm going to start int I equals 0, I less than s1.length plus plus I, for int j equals 0, j less than s2.length plus plus j, VI is unhappy with me for something in here, because I'm missing a closed parentheses up on the line above. Okay. Since we're having that issue, I'm going to compile missing argument line 18 to the vector. Okay, so now the code compiles. Obviously it's not complete. For each one of these elements, I need to fill it in. And there are two possibilities, just as there were above. If s1 sub I equals s2 sub j, well, then I'm going to use table sub I minus 1 comma j minus sub j minus 1 and plus 1, and that's going to be stored at table sub I sub j, because that's what I'm doing. I'm filling in that location. We'll come back and see something that's kind of a nuance to this. Maybe some of you have already noticed that we have a problem here, but we'll hold off on it for just a second. Otherwise, if they're not equal, then t sub I sub j equals the max function applied to t sub I minus 1 sub j and t sub j sub I sub j minus 1. I have that all correct? Okay. And that'll run through, and we just fill things up that way. Now, question is, what's the thing that's wrong? Well, you might notice I and j both start at 0, and both of these expressions involve accessing t at indices that are I minus 1 or j minus 1, which means we're going to be pulling out negative indices from the vector, and while it is going to be perfectly happy doing so, it's going to be undefined behavior, and who knows what the heck we're going to get. What we really need is we have to put some ifs around this. Because I'm going to have to do this in 3 different places to keep this looking syntactically happier, I actually want to write another function. I'll call it lookup. And lookup takes as its first argument a vector of ints. But we call it t, because that is the value from below we're going to be passing in. And then the 2 indices that we want to look up in there. And in this case, the only possibilities are they go negative. So if I is less than 0 or j is less than 0, return 0, else return t sub I sub j. By writing that helper function now, I can change this. Actually, let's undo that. Instead of doing a direct instead of going directly into t, I call lookup, I pass it t, I pass it the I minus 1, I pass it the j minus 1, like that. And the same thing down here. T, I minus 1, and j. T, I, and j minus 1. Okay. Let's try using our DP solution. See if I've typed everything in correctly. 5, which was the answer that I wanted. Notice that returned really, really quickly. What if I actually put in a BC down at the end of S2? Now I should get a 7 when I run it. Okay, so that appears to work. Now the last thing here would be the question of, well, what if I want not just the length, but I actually want the strings? Well, this array T, or this vector of vectors, or two-dimensional storage, the table that we're looking things up in, has the information that I want from this. And so I can actually write, we could write another loop in here and backtrack over that. So I'll do that. I'll come back for one more video, and we will add to this so that instead of just returning the length of the strings, it actually returns one of the possible strings that has that length.